Okay, hello, I'm Jared. I'll be giving you an introduction to spin waves and magnonics today. A brief outline, I will cover the physics of spin waves and magnons, some methods for excitation, detection, and the materials relevant in this field. And I'll conclude with an application. This case, it will be computing with spin waves. So, a spin wave is a collective excitation of a magnetically ordered medium. If we recall the single moment picture, and as we learned, its magnetization is described by the Landau-Lefschetz-Gilbert equation. If we ask what happens when we have coupled moments in a lattice, we can intuit what a spin wave is. The center figure shows a small deflection in the center moment, which then propagates to the neighbors. That would appear as contribution to the effective field for the neighbors, which is propagates throughout that way. The picture is somewhat simpler in the one-dimensional case. There on the far right, a one-dimensional chain of atoms. The spin wave is then just the precession, the phase of the precession distributed across the chain. Using Hamiltonian, well, I'll cover this first. There are two general interactions for why electrons coupled, or electron spins coupled in a lattice, exchange and dipole-dipole coupling. Exchange, although very strong, operates on a short range, and dipole-dipole coupling is relatively weak on the long range. If we ignore dipole-dipole coupling, because that kind of introduces an isotropic effect, we can then represent the system with a Hamiltonian of this form, which we use to describe for magnetic exchange in class, taking nearest neighbors and the ground state of the system is when all the spins are perfectly aligned, but if we perturb it, like this in our picture, and ask what happens when the spins are flipped, then we get a dispersion relation for this very simple case, which is quadratic. So yeah, wave packets of these excitations are called magnons. These are quasi-particles, which I will use both these terms interchangeably. So research in this field was at a high point between 1960 and 1980, following the discovery of yttrium, iron, garnet, or YIG. This chart summarizes its standings relative to other candidate materials. Notably, the magnon lifetime and propagation distance are orders of magnitude larger than the rest. YIG is a ferrimagnet with an exceptionally low damping constant, which is very important. And it'll show up in just about every application that I'll cover. So on the experimental techniques, the methods of exciting and detecting magnons run the gamut from strain to optical, and all the electrical tricks like VCMA, STT, and SOT. This bottom left paper was recently done and was the first to show significant magnon propagation across micrometer distances using STT. I won't cover that one in detail, but I will cover the one on the right, which is a much simpler example. It uses RF signals. The input antenna would have an oscillating RF signal, which would, if the frequency and orientation are correct, would cause spin waves to propagate to the output antenna, which would induce by induction current in the output, which is one of the simplest ways to excite and then detect spin waves. Bottom chart shows transmission. That F1 is just a ferromagnetic resonance, which kind of caps. When all the spins propagate in the same way, when it's uniform precession, that is a special case. That's ferromagnetic resonance. So applications and research topics are also very broad. One interesting one is Bose-Einstein condensates. Researchers have claimed to show, since magnons follow Bose-Einstein statistics, its theory says that they should condense, and researchers have claimed that they've shown this. I will not go into detail to that. Also magnonic crystals, which are the magnetic analog of photonic crystals. Photonic crystals have periodically modulated refractive indices, which give them interesting refractive properties. Well, an example is like opal and butterfly wings. So magnetic crystals, like that on the right, would be similar, periodically modulated magnetic properties. This allows for engineering of the dispersion relation, which is used in proposed devices such as this magnonic transistor. The more usual applications like computing and logic are also present. And today I will be covering digital logic in particular. Since magnons are waves, there are multiple ways in which you can encode information into them, or two being amplitude and phase encoding. To start, I'll look at amplitude encoding with a simple example. Oh no, it's covered here.
Okay.
Okay, with a simple example shown on the right, it is modeled after a Mach-Zehnder interferometer, which is that top right figure. A beam hits a half silvered mirror, which splits it into two interferometer arms U and D, which reflect back to another half silvered mirror onto a detector. If there's no phase difference, if the interferometer arms are the same length, all the light goes into detector one. If there is a phase difference, then you can measure the relative phase difference by comparing the amplitudes of detector one and detector two. So this device is experimentally shown XNOR gate. They also have a NOT gate and an AND gate, so that would make an interesting logically complete example. Operates in a similar way. An electrical signal splits, then propagates through a YIG substrate, which can then be phase modulated by those kind of currents that would just induce a magnetic field down below, which then collect and would interfere if there was a applied input phase shifted. They might either interfere constructively or destructively. Constructively, we would get a high amplitude, destructively, low amplitude. So this is an example of amplitude encoding. The bottom right just shows the truth table and the expected signals for the XNOR. Oh, okay. More interestingly, that was a hybrid example and relatively simple. This would be an all magnon approach using phase modulation. This is an inverter gate, just in this short example. So since the information is now encoded in the phase, if we just have a longer substrate, then if we have a node, we can make it so that when we have a node at the input, we get an anti-node on the output, thus inverting the signal. This is one of the most popular devices studied, a majority trident-shaped gate. It's mixed signal, which allows for chaining, but I'll come to that. Odd numbers of inputs will construct or interfere at the junction there. And for example, in the bottom left, if we have, say, 0, 1, 1, the 0 and the 1 would interfere destructively, cancel out, and then the one signal would propagate through, giving us this triangle, slightly amplitude modulated signal, with the one being a 180-degree phase shifted signal propagating to the output. This is experimental data with a very high frequency sampling oscilloscope. Device is shown there. You can kind of see the outline of the majority gate. And yeah, this allows for, with a bit of overhead, to couple multiple of these devices together, like in the bottom right, using a small nanomagnet to clock the signals between majority gate to majority gate. I will conclude there and take questions.